task, and you can see also some more complex tasks here that HRP is performing. But the thing is actually, most of these are actually pre-programmed. So basically, the robot here knows exactly all the interactions anticipated. So it knows everything and performs some pre-planned motion. And everything can be different during the execution that can make this robot fail. The only exception is actually what has been demonstrated recently from Petman and Atlas and Boston Dynamics, where actually shows first time that extreme, let's say, physical interaction between the robot and the physical environment to support balance and locomotion. So motivated for this, actually our goal is basically to develop a whole body soft humanoid for multiple conductor interaction that can actually have the skills to execute some of the scenarios that you can see here, where actually humans use the whole body, feet and hand to perform either balancing actions like here, where use the environment to conduct and create additional reaction forces from the strains of the environment to balance, or to perform, let's say, to switch between different locomotion modes from bipedal to quadrupedal and navigate through difficult terrain, so here in flatter spaces and so on, or perform powerful robust manipulation. So we have some history of the development of humanoids. So going back to starting going was actually 2004, so it's about 9 to 10 years ago, where we were involved in the Roboca project, started work on the design of the ICAP. We were mostly involved there on the design of the lower body and the waist. And this actually child type humanoid was ready, first prototype at the end of 2007. So moving forward after this, the end of this project, we were actually involved in another European project that was targeting to develop a kind of extension of the ICAP. Like an extension prototype that incorporates physical elasticity also and joint top sensing on the joints to achieve skills that allows the robot actually to perform reactive learning, interacting with the environment, and try different learning techniques that may need for the robot to have increased physical robustness. So this is actually the first legs of a combined humanoid command that were actually built back in 2010, and then a couple of years after we have the complete command humanoid, including now the upper body, missing still the forearm and hands, and also missing the head. So as specifications, I put this in line, which basically is actually to develop a humanoid that can physically interact with the environment at the whole body level. And is implicitly and actively adapted to conduct and impact. This means to have the physical robustness to cope with these interactions, and also be fast and reactive in performance and demonstrate robustness in operation. So the three key design features in command was actually basically the use of the moderate to high power capacity actuation. I will give you some numbers after on what you can achieve for this. Has increasing joint elasticity for physical robustness. And incorporate also joint offsets that allows to modulate the impedance of the robot at the whole body level. And we start from the ICAP template. This was actually a small robot of 1 meter, so this actually sets some constraints of the design. Since we like to integrate all the additional features of the actuation, like integration of top sensing and passive elasticity inside the same size of the robot as original ICAP. And also had a second question to answer, that developing such a multi-DOF series elastic robot, how to dimension, how to scale the compliance on the different on the different joints during the design phase. So here is an overview of the command, which basically, as I say, it has a moderate to high power actuation drives. Incorporates passive elasticity in the major joints of the robot. So we have on the legs, I will show you the next slide, in the torso and the arms, several joints they have the series elastic feature to provide the robustness. There are any cable transmissions, so the actuation is based on Brussels motor harmonic drive and series elastic element. We incorporate also the joint top sensing, so all joints they have additional joint top sensor, and we have also additional sensing, including the IMU, 2 IMUs, actually one at the lower body and one at the torso, and 6 DOF cross-top sensors that are at the feet, but will be finally eventually also at the forearms after we incorporate the forearms in the hands. The system has power autonomy, so it has a lithium-ion battery and power management system. We have actually one PC104 that's inside the torso, and the second one is inside the head. And that you can see is fully covered with no exposed wires and other cables. So this is the kinematic command. So in total now it has actually 30 degrees of freedom, including the neck. With in this figure, the red degrees indicates actually the ones that they have passive elasticity. So all the sagittal joints of the pitch joints of the legs, they have a series elastic element. The pitch and the yaw of the waist, it has also the series elastic element, and on the shoulders, the first two joints, they're all in the pitch, and the elbow, they have also the series elastic joints. So 14 of the 32 joints, they have the passive elasticity. The drive we use is actually something developed a few years ago in 2009, at the beginning of the Martian project, that is based, is a compact, let's say, series elastic principle that combines a frameless brushless motor with a harmonic drive and the series elastic element that is torsional, that is implemented using linear springs, using this kind of implementation. We have a full state measurement. We have 3 voltages that measure the motor side, the link side, after the gearbox, position, and also the link side after the elastic element. So we can get also the spring deflection throughout the measurement. In addition, there's a torque sensor that you can see actually here between the elastic element and the harmonic drive. Now this is also a long video that's showing the first prototype we built, actually demonstrating the active control on top of the passive elasticity. You can see later the effect of the passive during the impact. So the motor is actually is a high performance motor. We have a peak power of 470 watts, and it gives us the design was actually made to be conservative from the motor side. So actually, what is limit the torque on the drive is actually the harmonic drive. This means that actually even with the peak torque that you can have in the harmonic drive, we still have enough velocity capacity to perform reactive motions. The stiffness is, although I say it's actually fixed, it's not actually fixed. Actually depends slightly on the deflection. So you see that it has actually reducing is reduced actually with the deflection that is maximum up to 2.2 radians. In these units. This is the lower body, actually, particularly the leg, which is actually has 6 degrees of freedom, which is about 2 degrees at the hip. We have the thigh rotation here, the knee, and the 2 degrees of freedom at the ankle. The force of sensor is mounted down here between the foot plate and the ankle. Now, I'm not going to give you details, but only for this joint, particular joint, just to show you the numbers of the performance we get on the joints. So, of course, it depends a lot on the power supply, but you can see here that at the maximum voltage that you can drive the 48 volts, you can actually reach at the peak torque close to 9 radians per second at the joints. It is very, very fast compared to any other humanoids, at least electrical driven actually humanoid system. So this allows to, as I said before, to be very reactive and be fast when balancing and reactive to perturbation. Moving up to the upper body, it's the waist. Again, the implementation is based on series elasticity. I say already that there are 2 degrees of freedom, is actually the pitch and the yaw, that they have the series elasticity, and the roll is stiff made. And inside here actually is also have the mounting of the IMU sensor inside the house of the waist. Going up to the torso, this is actually forms basically the main housing of the communication unit that we have, the P104. Also, it has is a frame that supports of course the shoulders with the first degree of freedom, the pitch. We have also the 2 degrees of freedom neck, which is based on the power structure, and finally the battery system with also the power management system at the bottom here. Now the battery is actually lithium polymer. It weighs 1.70 kilogram. It has actually energy density of 180 watt-hour per kilogram. We did this exercise actually just to demonstrate how long we can last, and actually basically the robot we did this light duty squatting for 2 hours and 12 minutes with this battery on board. Moving up to the arm, the arm currently actually has 4 degrees of freedom. It has 3 at the shoulder. 2 of them are series elastic, the pitch and the roll, and also the elbow is also series elastic, while the rotation of the upper arm is actually stiff. Now for the wrist and hand, we actually these are under development at the moment. We have actually designed the forearm here to 3 additional degrees of freedom for the wrist, while for the hand we are adapting actually the this IIT hand that was presented before from based on this soft synergy, first synergy concept, using a single motor, and this hand is actually under construction now, a miniaturized version to fit the scale, body scale instead of Coleman is under construction, and we expect to have this by the end of the summer together with also the forum. Now, let me move to also the part now that is, I briefly mentioned at the beginning that was one of the problems we had actually during the design, or one of the challenges were basically how to design where to place the compliance, and then how to select the joint compliance level and scale it across the leg and the out joints. And of course, for those that have actually know the details about the elastic robots and joints, there are very easy information on how you can do this tuning, and most of the times actually, especially for multi-core system, this is done on the basis of the trial and error process. People, they try different stiffness levels, and then they try to match this to some kind of trajectory properties, frequencies, and so on. So in common, basically we have this way, we wanted to ask this question if it's possible to tune this compliance using a more systematic method. So basically what we did in common to set this, I will give you the example, for example, the legs, is actually to perform a modal analysis of the overall body of the command using a slightly simplified system where actually the upper body is considered single mass, concentrating all the mass of the upper body, and then decide for certain resonance that we want to set, and based on this resonance constraints, then find the optimal stiffness of the joints that satisfies the resonance constraints. So of course, this is a nonlinear system, and in order to perform this, we actually will consider a single cycle of the phase, and consider 20 discrete points in this phase where we actually linearize the system. Then starting from the flexible joint dynamics and some manipulation, change the variables, also including the Jacobian of the gravity vector to add the effect of the gravity to the stiffness metrics. You end up actually with a system that actually in the form of spring mass system. We also can incorporate some active control and gain here, which is like a simply proportional gain, that you can actually get the resonance of the system for this 20 equilibriums, and as a function of this mass and stiffness metrics. So following this, then we form a constraint optimization program where basically is actually to select the stiffness that satisfies the certain resonance for the system, but actually trying to select the softest solution that actually satisfies the resonance constraints. So we use this kind of function that is actually the inverse of the energy that you can store in the joints of the leg. This is the ankle and the knee and the hip stiffness. And then we have a number of constraints that we have to set the different natural frequencies in specific brain, in specific level, and also a number of additional, let's say, constraints, linear inequalities that came from the actual design here. And this is actually specifies the minimum passive system we can put on the joint that we actually selected, considering the maximum torque that we can get on the joint and the physical maximum deflection we can have. So basically, we say that we cannot actually drop the stiffness below a level that will reach the limit of the spring deflection before the maximum torque is applied to the joint. While the second Kmax was actually because of physical constraints and limitations to keep the size of the joint. So here you can see, for example, for setting we set the first two resonance, actually the first 1 Hertz, and the second 3 times higher than this. Basically, the principle that we want to actually have the first resonance far from the second, so in case that we want to exploit, let's say, the natural dynamics, we can actually exploit, we can stay below, but at the same time, the second resonance is actually higher enough, so that does not actually interfere with the first resonance. And here you can see the stiffness that we can get actually from the 3 joints of the hip and knee and ankle. You can see the nice scaling, let's say, increasing the stiffness from the ankle going to the knee and hip, and the same result you can get also for the arms, let's say, from the shoulders giving higher stiffness, elbow lower, and so on, going down to the wrist. And this graph shows actually the result and the natural frequency, how they set. So we have the first on 1 Hertz, the second on 3 Hertz, and the others are higher and not relative for the locomotion. So I'll show you some videos to show the performance we get first from the impedance controller, robot impedance and torque control. Okay, the first phase of the video, you see basically the robot is controlled using impedance control at the limbs, the legs are more stiff, and then the arms are more soft, so people interact and pull the robot away from the equilibrium. And of course, you have the basically what you can see also from the work presented before from Ali, and also other manipulations like Luca, where you have this joint torque and impedance control capability. Now later in the video, you will see, I forgot to go fast. Yes. Okay, here you can see actually the arms are still impedance control, but actually the legs are zero torque control. So we try to track zero torque on the legs, so basically this becomes completely back driver, and you can basically follow the natural dynamics instead of the system. In the second phase, you can do basically the upper body, and the legs are just following the zero torque reference. In this video, you can see also some of the walking gauge generation walking that is actually based on, not based on ZTP, but based on center of mass cycling motion generation. I will not give details on this, but I'll talk more about the balancing later. Okay, let me give you some details now on the assembly balancing and the work we did actually on the balance stabilization for against the pushing disturbances, which basically is in total, you can describe as basically two main strategies that we call it center of mass compliance control and upper body attitude regulation. In overall, actually, the reaction we get is actually that you basically make the first strategy makes the robot to be compliant, actively compliant on top of the basic elasticity during the impact in order to absorb the impact. And while the second strategy actually moves the upper body is upper body strategy that moves in the direction to compensate certain effects that are generated because of the back-off motion of the first strategy. In overall, actually, this resembles the reaction that you see usually in the martial art, for example, where the person is expecting to get say a punch, then you actually back off in order to reduce the injury and use your upper body to stabilize this back-off motion also. So for the center of mass compliance regulation, actually the control that is coming line is actually kind of admittance control. So at the time that we implemented, we have get the joint torque sensing. So it's actually an admittance control that we implement on center of mass using the ground reaction force torques. So basically, you can using the simplified model, model, you can actually set the desired impedance at the center of mass, and then produce perturbations for the angle of the inverted pendulum from the equilibrium position. Okay, this expression of the equilibrium is considered at the zero in order to satisfy this impedance. As I say, it's admittance control, but of course you can implement now with the joint torque sensing value, you can do it also with impedance control. Now the second strategy actually is kind of angular momentum reduction, say, I would say conversation, but it's not actually is an approximate actually method. So what we did actually is basically to scale the ratio of the velocity of the upper body in the opposite direction of the lower body on the basis of the two inertial tensions of the upper and the lower body. So this is very fast, can be implemented online very fast. And so the robot is split into two bodies, actually the lower body and the upper body. And then the motion that's generated from the upper body is complete, as I say, by scaling the formation of the upper body with the angle alpha here, with the scaling of the two inertial tensors, with the bottom includes basically all the lower body up to the hips, excluding the feet, and the upper body is actually all the torso and the arms segments. And this will basically generate this kind of action. So basically, due to the first, let's say, strategy, the robot will become compliant, will back off back, but actually the upper body they will move forward. Serving two purposes. First is actually to bring again the center of pressure further from the back edge, but at the same time is doing some kind of also angular momentum compensation from the one that is generated by the lower body. So this is actually some video that shows basically the performance. You get this with the robot in the say stepping at stance. And this is actually a robot that is the first prototype we developed, and now it's actually at the TFL, in the group of Pittsburgh. And this was the day when we deliver actually the robot and do this trial and take this video. You can see that actually they can absorb quite hard impacts actually, and some of them actually go on the single leg. You can see the passive elasticity of the arm, how it protects actually to reduce the impacts to the main body. And you can see the effectiveness of the method. In the next video, you can see also the effect of the upper body strategy and the robot control and how it actually the upper body moves in the opposite direction of the deflection of the lower body to save the effect of the impact strategy. Let me show you also some recent work. This actually will be presented next IOS, which extend the stabilizer in order to consider now also IMU feedback and do estimation of the terrain inclination. So in the first videos that we saw, basically everything was done with using only the ground reaction force sensing without any IMU sensing. While here we use also additional the IMU to detect also the terrain inclination and adapt to this. We're also extending this to the stabilizer and to the two different directions. In the picture on the left, you see basically a stepping strategy that we add on top of the stabilizer, where the robot actually decides and takes a step on the basis of the level of the disturbance. And you have implemented this so far on only the lower body of the system. You can see the reaction that you get with the robot taking steps under as a reaction to the disturbance that's applied by the person on the back. Now on the right side, you see basically the involvement of the upper body. You can see let's say a multi-contact case where actually the upper body is actually is controlled to provide to demonstrate the first principle of how to use the arms to balance against the when you have a let's say how do you effectively use the constraints of the environment to generate additional reaction force to balance the robot. The principle is very simple, basically demonstrate basically the principle mostly, but the selection is actually limited to the plane at the moment and basically selects the contact point of the wall in order to make the arm in that direction, in the direction that the disturbance the most compliant configuration. Now let me move to basically maybe speculate a bit now on the benefits that we get from the compliance actuators and also maybe speculate on some challenges that we still need to to demonstrate there, but really we can actually benefit from this kind of actuators. So so far there are several works that shows that basically the compliant actuators can give you the intrinsic robustness. It can make the robot to be more robust against the impacts and so on by reducing the impact force that reaches the drive system, preventing, let's say, the breaking of the induction drive and so on. Of course, it's also passively adaptable to interaction, so any force that will be applied to the body will make the deflection on the body. This basically makes the robot adapt to this kind of interaction, and allows you to do also high fidelity force control. There are also several works with CLPs and also DLR that demonstrate that you can actually have additional power output from this kind of actuators by doing, let's say, making use of the energy that you can store inside the spring to increase the velocity at the link side. Now, what I would like to want to speculate the same comment is actually about the energy efficiency that actually very often it was reported actually in many works that actually these type of actuators can actually generate, can demonstrate energy efficiency by using the natural dynamics, exciting the different frequencies and so on. So of course this can be really demonstrating a single degree of freedom system. You have done some work in the past with the actuators that does stiffness our DSA, let's say, joint at IIT, where basically we set the stiffness to the natural frequency of the system to the frequency of the input trajectory. You can actually really demonstrate that you cannot execute the trajectory with the low energy consumption. Of course, this is very obvious and it can be done, as I say, in a single degree system. But there are some actually limitations that you start facing when you start considering, let's say, the real system and what is actually the capability of the existing actuators. And I would like to point to, which is basically, the first is actually the energy store capacity in most of the implementations that are actually done so far is very, very limited. So the best performing joint that I think is actually the VLR VSJ joint on the arm. You can store an amount of energy that is 4 to 5 joules. And this is really, really tiny amount of energy if you consider the energy required to move a system like the arm they have. The second actually limitation is actually the small passive deflection we have on the joint. This means that actually you can actually exploit the natural dynamics, but you can actually exploit in very, very small range. So we have joints that they can actually have a range of deflection that is about 0.2, 0.3 radians. Whatever you can do further than this, you have actually to move the main motor. So this actually, you can see it here, for example, for us. We demonstrate actually that this actually can improve the efficiency, but actually the deflection of the link was actually limited to 0.2 radians, because this was actually close to the limit of what we can get from ours. If you try to increase, and you can, of course, demonstrate that you can do the motion of the link, and you're going to have a very minimum motion of the motor that basically compensates only the friction in the losses. So what happens actually if you want to increase this range of motion, then of course I need to move my actuator, and this implies that actually additional, let's say, limitations which are related to the high gearing and the large actuation inertia that we have still in all this implementation. So basically, a lot of the energy, a big amount of energy that you consume during the motion is actually just to accelerate the inertia of the motor. So still all the VSA joints and most of the series elastic are based on, let's say, moderate high gearing, and this increases a lot the inertia. And of course, if you consider this, then you see that the small energy capacity that you have to store in the joint is very little to provide you energetic benefits. Now, there are some, of course, series elastic joints that they have additional, let's say, large capacity producing very soft elements, but then you start facing the problem that you control difficulties, you have bandwidth limitations, and so on. So, one, actually, you can consider also the additional mechanical components. Of course, let's say to judge if an actuator is more energetic efficient, you have also to judge, I guess, the rigid case where actually it's probably will be lighter and including less mass components, while here you have to add the additional element, the spring element, and so on. There are also additional factors, for example, the damping control. I mean, Alan mentioned before that you can actually, in this joint, you can actually also regulate the damping in order to prevent the oscillations that you may need sometimes that you need accuracy. This actually will deteriorate the efficiency because this will use more energy. So based on this, actually, I will give you a common example where we did basic simulation, showing some of the energy that we need actually to perform this action. This is actually for both legs. So you can see the energy that you consume for the knee, the hip, and the ankle while doing this floating motion up to a certain frequency. And you can see that actually for the knee joint, you need something like 75 to 80 joule of energy to do one cycle of this for one hertz trajectory. Now, if you look this one, if you compare this with the energy you can store actually on this series elastic element, which is actually in the order of 1.5 to 2 joule, then immediately you can see that you cannot do much by recycling energy in order to improve the efficiency. So this actually motivates us to work in a new concept of combined agonistic joint that is very, very recent work. That basically the principle is actually how we can combine an actuator that has a large energy store capacity, but at the same time you can actually control. So basically combine a series elastic that has a soft elastic element with a large deflection with an additional actuator that allows also to have good control on the joint. So the design specs were basically these three: high power performance, large energy store capacity, and physical robustness. So we end up with this, let's say, arrangement, which is, we call it asymmetric combined antagonistic scheme, and it's based actually on the two drives. We call it asymmetric because the two branches actually have many asymmetries, let's say. So here we have, let's say, a series elastic element on the motor M1 that is basically there only to provide the physical robustness of the joint, and also used as a reflection sensor to measure the torque. But it can store only very little amount of energy. On the second branch, we call it energy of storage branch, and you have a type of spring that can allow you to store a large amount of energy on this elastic element, driven by actually almost a direct drive motor that needs to work at peak power for very short distances, while combined with the normal drive coupling allows you then to be, let's say, released by the effort required to keep the tension of the spring, and basically become efficient by using springs to do variable gravity compensation and so on. So this is another secret. This is actually a small drive that is actually almost, as I say, direct drive. Well, this is actually a motor, is a high performance motor, but again, we use a low to moderate gearing. It means that 50 to 1 up, that allows to be also, to reduce the inertia. As I say, this is one of the factors that limits the, let's say, what you can get from efficiency of these combined actuators, reduce the inertia of the main motor. So some details. So this is actually a prototype that we do to demonstrate the principle. This is the high performance branch, which is based on the brushless. It's a custom motor that we made. It can operate at high temperatures. We have a peak power actually of 2.8 kilowatt, and it's very compact. Actually, the unit weighs actually 1.4 kilograms, and use a principle of torque sensing that is based on the torsional bar and the absolute encoders before and after. Now, the energy branch is, as I say, based on a very efficient drive, so it's actually a bore screw with a long pitch. So it's actually 1 centimeter pitch that allows you to be completely back drive up. You can actually do fast application of the elastic element that store the energy, and at the same time we use the coupling with these two side overriding lugs that allow us to block, to stop the backgravability from the spring. Now, in order to allow to store the big amount of energy, we don't use metal springs. Because this is actually heavy, and really, if you want to increase the energy that you can store, you need to have a large strains on the elastic elements. So we use a type of rubber springs that you can see actually here that allow us to store, you can see in the following graphs, a large amount of energy. So this is some of the performance, let's say, curves that we get. So in terms of energy storage, we can actually, the joint can go up to 120 joule of energy for the maximum deflection of this energy branch, and provides also additional torque to the main actuator that can reach actually for maximum deflection up to 70 millimeters. So this shows a first demonstration of how this let's say joint, you can actually, this elastic element in the second motor with the variable retention, it can be used to reduce the instantaneous power that is delivered by the first motor while this leg was executing the hopping was 2 Hz. So basically, this is a single hopping experiment where the equilibrium of the energy balancing branch was varying slowly within its range. And you can see actually, of course, by varying as I say manually, was not any control running to adjust this. You can drop actually up to 20-25% the instantaneous power that was used to execute the same trajectory by simply adjusting the representation on this elastic element. And I will close with this video, first video of this prototype joint that demonstrates actually the principle. So the main actuator is controlled under proper impedance control. You see the representation of the elastic element there. And later you can see also the system robustness where we drop it almost half meter while you do the hopping. And measure here that there are actually 15 kilograms weight on top of this leg. Okay, so just to close with acknowledge the common thing.